Good morning, good day, and good afternoon, and good evening, everyone, wherever you are. My name is Domagoj Jakobovic, and with the help of Marko Đurašević, my colleague, I will shortly present you our work on applying genetic programming in the hyperheuristic approach for dynamic scheduling problems. Now, many people in our task force group are very well acquainted with what I'm about to present. So some parts I'm going to cover much more loosely, some parts I'm going to go into detail, but at the end, of course, there is opportunity for any kind of questions if you are interested about something. This presentation is going to be divided in 4 parts. First part, I will shortly explain on what do we solve. Of course, it is related to scheduling, and we are all very familiar with scheduling here, so I'll just skip over those introductory parts and then say something about how do we solve the problem, what is the performance that we could expect from this method, and where else can this approach be used. Well, in a nutshell, what we actually have is a problem, a scheduling problem that we want to solve. And this scheduling problem may be presented in a number of learning test cases that we have available some way by synthetically or derived from a real world experience. We also have some scheduling criteria that we want to fulfill. We want to design scheduling algorithms that optimize certain criteria, or single or many of them, or multiple of them. Also, we have a schedule generation scheme which dictates what activities can be scheduled at a certain point in time, but we still don't have the answer of what particular specific activities should be scheduled. And there we apply the magic of genetic programming by principles of simulated evolution, and genetic programming obtains us a priority function which actually decides what activity to schedule at a certain point in time. Then, when we have a custom evolved priority function, we also use the schedule generation scheme and that priority function to basically have our own new derived dispatching rule. And that dispatching rule is then used on new unseen real-world test cases. And that is the basic idea. So that's it. Now you know everything. But of course, I do have some other slides to show. So this is actually the main idea. Of course, we do solve all different kinds of scheduling problems, and you all know that they vary very much. But all problems consider allocating activities or tasks or jobs to certain resources that are usually called jobs and machines in the scheduling theory. There are many different examples. We have tackled models for manufacturing, from workforce allocation, warehouse management, and so on. Now, different scheduling environments differ according to machine environment, the criteria that we want to optimize, additional constraints, if there are any, and additional scheduling conditions. Among scheduling variants, the most primary mean of dividing them is probably according to the machine environment, to the resources that we are using. In that case, in that regard, we have a single machine environment, parallel machines, and multiple stage environments such as flow shop and job shop. We will concentrate on the environment of the parallel machines as a showcase in these presentations. However, we have applied this principle to other environments, and of course, the principle itself is quite general, but we will talk about parallel machines as an example. In a parallel machines environment, we have a number of jobs that need to be scheduled on one of the number of available machines. For every job, we have a defined set of properties. How, for instance, the processing time of a job on a certain machine. How long does machine I will process the job J? Now, it is important to note that in this environment, we do not assume the proportional speeds of the machines, but the processing times are completely unrelated between jobs and machines. For instance, for any job, a different machine can provide the minimal execution time, the processing time for a certain job, and some other machine for other job. Each job has an importance, a weight, it has a release time, it has a due date, and it may have other properties that define its behavior and that should guide us in the decision of when to schedule that job, among others. There also may exist several additional constraints, like the setup times, times required to adapt the machine for a job after one type of a job is finished and then another type of a job needs to be scheduled. We may have precedence constraints. Some jobs cannot start before others finish. In questions. What we actually aim to accomplish is to optimize some criteria that we are trying to schedule for. The most common criteria are listed here. For instance, there is total duration of the schedule, which is called make span. There is total flow time, total time the job spent in the system, total tardiness, the amount of time the job spent. That combination of criteria that the user may want to have solved. And in that case, our approach is going to help us a lot. Now, although we are familiar with the scheduling theory, I'll just detail the scheduling conditions that we define to have when building a schedule. For instance, regarding the parameter reliability, we may have deterministic or stochastic scheduling. In a deterministic system, all system parameters, the job parameters, the job machine properties are known exactly. In a stochastic case, those values are can only be approximated by some distribution. Regarding parameter availability, in an offline case, we presume that all parameters are available before the execution of the system. So we may build the complete schedule beforehand and then just run it, and then just the system will go. On the other hand, in an online setting, which is what we take by default here, system parameters become available only during the execution of the system. For instance, the job properties are not known before the job enters the system. Only when the job has entered the system, only then we know its parameters. Or the parameters can change during the execution. And finally, schedule construction can be static. In that case, the whole complete schedule is constructed before the system begins its execution. And this is, of course, applicable only with the offline scheduling. And the schedule construction can be dynamic. That means that the schedule is built incrementally in parallel with the execution of the system. As the system is executing, new decisions are made at each decision point to build the whole schedule. And this is actually the setting that we are going to concentrate at. So what do we presume in dynamic scheduling? We presume by default the online availability of the properties, so no information is known beforehand, before the job arrives in the system. And the schedule, of course, in that case, needs to be constructed simultaneously with the execution of the system that we want to simulate. In this case, of course, we need to be able to obtain the scheduling decisions quickly. So the speed of the construction of the schedule is an important criteria. How do we solve scheduling problems? Well, we all know there are different approaches to this. We can have exact algorithms, we can have approximation algorithms, but they have properties that usually don't make them applicable in these dynamic and online conditions. In that case, we may also use heuristic algorithms, which are applicable for various criteria and various conditions. They do not guarantee the finding of the optimal solutions, but they are very useful in practice. There, we may have two different approaches in heuristic algorithms. We may have improvement heuristics, like genetic algorithms, that start with a complete schedule and then iteratively improve the schedule over time until we reach the satisfying level of quality. On the other hand, we have the constructive heuristics that incrementally create a schedule decision by decision and only at the end come to the complete schedule. Because we are dealing with the dynamic environment, we will concentrate on constructive heuristics in this case. And one notable example of constructive heuristics are dispatching rules. They are simple heuristics that at each scheduling decision determine which job should be scheduled on which machine. Their advantage is that they quickly react to any changes in the schedule, arrival of new jobs, the change of the properties of the jobs, breakdowns of a machine, etc. And to determine which job should be selected at a certain point in time, the dispatching rule uses a component called a priority function. And the priority function actually defines the priority of each activity of each job that could be scheduled, and we decide upon the job which has the highest or the largest priority. These are some notable examples of used priority functions like earliest due date, weighted shortest processing time, etc. For instance, let's say we have this priority rule that we have obtained somehow that defines the priorities of jobs to be scheduled. And at the current point of time, which is 0, we have 2 jobs available that could be scheduled in our system. According to the parameters of these jobs, they are known because jobs are already available, we have calculated their priorities. And we select the job to be scheduled according to this priority value. Now we choose the job with the largest priority, but the largest priority could mean a higher value, or it could also mean a lower value, depending on the design of your system. In this case, for instance, we choose the job with the lower priority value as the highest priority job, and we schedule job 1 because it has a lower priority value than job 2. By the time job 1 has finished at time 10, we still have job 2 waiting, but in the meantime, another job has appeared in an online setting, and these are its property values. According to our priority function, this job has a lower priority value than job 2, so we will select him instead of job 2 to be scheduled next. And finally, after the job 3 finishes the execution, we have job 2 with its priority. Notice that its priority has already changed because of the elapsed time, and the priority is dependent on the time. Its priority gets larger and higher and higher, which is actually denoted in this lower value of the priority function. And finally, job 2 gets scheduled. Now, how do we make the schedule? Any dispatching rule basically consists of 2 parts. The first part is a schedule generation scheme, which defines the set of jobs that are eligible to be scheduled, and a priority function that actually decides which job is going to be scheduled at a certain point in time. So the SGS decides how the schedule should be constructed, and SGS also takes care about constraints and idle times and other things about the schedule construction. But the priority function is the central component that defines which job is going to be scheduled. This is an example of a schedule generation scheme, which just repeats while there are unscheduled jobs, we wait until at least 1 job and 1 machine are available. We calculate the priority for scheduling each job on each available machine, and then schedule the job with the best priority on a machine if it's available. Okay, so we have dispatching rules available. We do use them in practice. However, there are issues here. For instance, performance. We can always ask ourselves, okay, is this dispatching rule the best fit for my scheduling problem with my scheduling criteria? How can I improve the performance? They are difficult to design and choose manually. There are a plethora of dispatching rules available. Which one should I choose for my scheduling problem? In some cases, this is trivial. In some cases, it is not. If we want, we could try to design new dispatching rules, but it's definitely not trivial. And this presents a problem. So the main idea here is that we can use a hyperheuristic approach. We search the space of heuristics instead of space of solutions, space of schedules, to find an appropriate heuristic to be applied to the whole set of instances of our scheduling problem. So this is actually the main idea. How do we solve that problem? How do we apply hyperheuristics? Well, we apply the magic of genetic programming, GP. GP is an evolutionary algorithm used for optimization and machine learning. In genetic programming, we actually try to evolve computer programs. So the individuals in a population that GP maintains represent computer programs, or if they do not have any side effects, they are just mathematical expressions or functions. Inner nodes of our we usually use syntax tree form in representation of the GP individuals. In inner nodes, we use basic elementary functions such as arithmetic, Boolean, logical functions, etc. And leaf or terminal nodes are variables and constants that are available to our problem. For instance, this expression could represent a priority function for some conceivable problem to be solved. And here it is represented as a GP individual in a tree form. Okay, so how do we design dispatching rules with genetic programming? Well, the schedule generation scheme is usually defined manually. So this part is usually defined manually. And what we evolve with genetic programming is actually a new priority function, a mathematical expression that defines the priorities of jobs to be scheduled. How do we evolve it? Well, we need to select an appropriate terminal and function set to allow GP to build a good priority function. We may use different kinds of function nodes. We may use different kinds of terminal nodes. And this is specific. This is a feature of every machine learning approach. We need to select features for a machine learning technique to combine them and produce a result. In this case, priority function. We may use simple terminal nodes like processing time, current time, due date. Or we may define some more complex terminal nodes, complex features like slack, timeout in the machine, which can process our job the fastest becomes available, the remaining time until that machine is occupied, and etc., etc. So what is an appropriate terminal set? If we have more terminals, we have more expressions, but that is a larger search space. If we have simple and smaller number of terminals, then GP wastes time to obtain good sub-expressions to use in construction of the priority function. We can manually construct and select features, but it's slow and time-consuming. And rather, there are techniques here that introduce automatic or semi-automatic feature selection in the search process. For instance, we can select features by importance based on preliminary runs to see which features are used most and which are not. We can construct new features during the evolution. That is also possible with genetic programming. And we can also employ a two-stage approach, where in the first stage, we just evolve rules to determine useful features and then use them as sub-expressions. Those expressions are used as terminals in the second stage. So this also helps. How do we evolve appropriate priority functions? Well, we need to have a training set which contains predefined problem instances, or it could be a stochastic generation of new problem instances during the execution, or we can just cycle through the set of our instances in order to try to increase the generalization ability. Of course, we do have a test set, and it is used for evaluation of our evolved priority functions. Now, in the fitness function, we need to ensure that all problem instances have the same influence. Because of differing number of jobs and different number of machines, we usually use a weighted sum of instances with different sizes to ensure that all have approximately the same influence. Okay, we do use GP mainly, but it is definitely not the only technique that can be used here. We may have many different variants of GP and other representations to be used. For instance, we may also use a neural network. We may use gene expression programming, Cartesian genetic programming, and grammatic evolution. This is also represented here, and many other variants are possible. What are its advantages and disadvantages? Well, GP is probably the best known and most commonly used here. Neural networks could also be used, but they are not that easy to interpret compared to GP. And we do have experiments with different GP representations in this case. And in our experience, actually, the tree-based genetic programming usually offers the best performance, at least for the combinations of criteria that we have tried on. With GP, we can evolve the priority function in its arithmetic representation form. However, this is not the only possibility. We can also evolve a function for selecting which existing dispatching rule should be used in a specific scheduling case, which is a decision tree-like representation. Also can be handled by GP. We can evolve a new priority function, which is this also called an arithmetic representation, and we can have a combination of both, like a decision tree, which can select an existing dispatching rule or can design a new dispatching rule within the same expression. But the most commonly used representation with genetic programming is the middle one, the arithmetic representation, where we just evolve a new priority function. So that's the main idea. Does it work? Is it any good? Surprisingly, yes. Because in most applications, it routinely outperforms manually designed dispatching rules that are available for specific problem variants. And of course, when there is no available appropriate manually designed dispatching rule, then this approach has also the greatest benefit. However, will it always be so? Of course, there are always cases in which our custom evolved dispatching rules with our custom evolved priority functions will not perform that well. So there are, of course, many different approaches that have appeared in the last few years how to improve the performance of this approach. We may try to improve the evolution, the genetic programming elements. We may introduce surrogate models. We can also include ensemble learning, and there are some other techniques I will not mention here because of the time. But I will just mention some most notable ones. For instance, in the improving of the evolution algorithm itself, we may try to employ a different selection mechanism that evaluates how different priority functions excel on different problem instances and try to maintain a diversity in our population to have a priority function that will solve any problem instance in the most effective way. We may have adaptive recombination operators that use a decision vector to characterize the behavior of a subtree when building a schedule. And we then may calculate correlation of subtrees within a tree to select appropriate crossover points and to actually obtain better offspring within the evolution process. We may also use fitness landscape analysis to obtain fitness landscape features of the problem, the scheduling problem we are trying to solve, and then apply those findings to tune the hyperheuristic parameters of our evolution process to improve the convergence and to improve the quality of our obtained priority functions. Because this is a trial and error process, and each candidate priority function needs to be evaluated on a number of problem instances or scheduling instances, this is usually slow. Of course, it is done offline because the priority function can be evolved offline before the system execution, but it still takes a lot of time, especially for difficult problems. So many instances need to be used in the training set to increase the generalization capability of the rules that we are trying to evolve. The solution to that can be surrogate models. In a surrogate model, we use simple scheduling problem instances to estimate the quality of our generated priority functions, and then only the best candidates are evaluated on the actual hard scheduling problem instances. And of course, we can also use a subset of instances in every generation, possible with instance rotation, all in the aim of reducing the computation time, but at the same time, in the aim of trying to increase the generalization property, because if we train on differing moving target instances, then we hope that our priority functions are going to learn to generalize better rather than having a static set of learning set instances. Advantages of this approach is that we have usually better convergence, at least on the training set. We have simpler rules, and we do have some improvements in execution time, which is always nice to have. When making a schedule, we do not have to rely on a single dispatching rule, on a single priority function. Instead, we may take a lesson from machine learning and try to use multiple priority functions to reach a better decision, which is ensemble learning. So, since a single heuristic will rarely work well across all the different problem instances, we may collect dispatching rules into ensembles and use them all together to perform a single scheduling decision, which hopefully should be better than each individual decision of each individual rule. Now, when we plan to use ensembles in scheduling, we need to define two approaches. First, how to construct an ensemble, or what rules make up the ensemble, or how to group them. The second decision is how will the rules in an ensemble collaborate. That is to say, how will they make a single decision based on all their performances based on multiple rules that are available in the ensemble. These two questions have different answers of how to construct and how to use the schedule to collaborate in obtaining a scheduling decision. For instance, to construct ensembles, we may use some existing methods from other machine learning techniques like bagging or boosting and cooperative convolution. However, in our experience, a method that we proposed, a simple example combination, which relies on previously evolved rules. We just pick them apart and combine schedules in a large number and just select the ones that perform most efficiently on a separate set of learning test cases. This is very simple and very efficient and provides ensembles of a different size, whatever number of rules we want to have in an ensemble, and we provide the most usually the most quality ensembles this way. We may also use meta heuristics to optimize which rules will form a single ensemble. For instance, a genetic algorithm may use like a feature selection, a rule selection to be included in a target ensemble. When we have an ensemble, then we have different ways of aggregating their decisions into a single scheduling decision. We may use sum of their individual priority values. We may have voting, weighted vote, weighted sum on different variants of these. In this case, we try to achieve a majority decision that will be more robust in applying to when applied to different scheduling instances that we have not seen before. Another approach is, okay, instead of combining their decisions in a single decision, we may allow each rule in an ensemble to build its own schedule, regardless of other rules in the ensemble, and then just select the schedule that ultimately turned out to be the best one, which is readily applicable in offline, but also can be applied to the online scheduling variant. For instance, in the sum combination method, we may have these rules, these priority functions that form our ensemble, and according to the different jobs, job 1, 2, and 3 that are available to be scheduled now, this priority function will produce these priority values, the second one these priority values, and the second one these priority values. So these are 3 priority functions, and in the rows we have priorities for different jobs, job 1, job 2, or job 3. The simplest combination method is just to sum all of these priority values and obtain a cumulated priority value for each job, and then just select the job with the highest priority value. The other combination method may be vote, where we obtain the same priority values as in the previous case, but we do not sum them. We just allow each priority function to vote upon a job that the priority function wants to have scheduled, and we just collect the votes, and we see that job 3 has obtained the largest number of votes, and we just select it for the execution. Ties, of course, appear here in both in and some combination methods, and there are different methods of resolving those ties, but I will not go into details here. What is important to note that the ensembles almost always universally outperform single scheduling rules. So it is, in our experience, always good to use ensembles to perform scheduling decisions. The results that the ensembles offer are not only better, they are less dispersed when we see their performance on the test cases, on the test scheduling instances. So their performance is more robust, and they tend to generalize better than individual rules. Okay, so there are other techniques which I skipped here. but they all aim into the improvement of the basic approach that I explained before. And there are many papers in the last few years, and there are many ways to try to improve the performance and try to obtain better quality solutions and better quality dispatching rules. But where can this approach be used? It can be used in online dynamic scheduling setting, which I've already talked about. However, this can also be applied in different environments, in different scheduling conditions. Although we have used dynamic scheduling as our showcase, this approach can also be applied to static scheduling problems, in which all the system parameters are available beforehand, and we can build the whole complete schedule before the system starts with its execution. In this case, we can still use dispatching rules, but they should be able to use all the information about the problem, about the future of the system that we are trying to schedule. Approaches in this case include adding static terminal nodes in GP evolution. For instance, they represent information that is usually not available in online, in dynamic mode of work. We can calculate priorities for all the jobs that will arrive in the future, for unreleased jobs, and this is called the look ahead, which can differ with the scheduling horizon that we take into account. Of course, while we still have time to build a schedule, we can build a schedule once using the dispatching rule, and then after the schedule is complete, we see what decisions were actually good and what decisions were not that good, and then we can use that information to rebuild the schedule again, and we can do that several times until we have convergence. By using the information from previous iterations of our schedule, we may build better schedule in the next iteration. Finally, we may use a simple rollout principle, which just at each decision point takes all the possible jobs to be scheduled and tries each one of them. We make a schedule with each job being selected at this decision point. However, in all the rest of the decision points, we use the best option only with only with our dispatching rule. And in this case, we at each decision point we build not one, but as many schedules as there are jobs that could be scheduled at this decision point. And then we just select that job that resulted with the best overall complete schedule at the end. This is of course timely, but it can obtain very good results. And when we apply these approaches to this method, then we can match improvement heuristics like genetic algorithms and other meta heuristics in building our schedules. In this case, we obtain a nice Pareto front of different trade-offs between execution speed, which is presented here on this axis, which is the time needed to build the schedule, and the schedule quality, less is better in both cases, for different approaches. For instance, here is our original approach that is very fast, but actually the worst one regarding the performance. And here we have an example of a meta heuristic genetic algorithm that has been used a lot of time to build schedules for problem instances. However, we have here, for instance, our approaches with the rollout, with the look ahead, that build the schedule that is even of better quality than genetic algorithm and takes somewhat less, practically the same amount of time as the genetic algorithms. And in between, in this nice elbow area, we have some trade-offs that we can select regarding what is more important to us in different scheduling conditions. The benefit of these approaches is that they are still applicable in dynamic environments where we may expect some job properties to change, because we still are generating the schedules incrementally in this way, rather than meta heuristics that use the complete schedule and improvement. Of course, There is rarely a single scheduling criteria that needs to be satisfied when building a schedule. So in most cases, in real world problems, we have not single, but multi-objective problems. So several criteria need to be optimized. We can, of course, use this approach to evolve custom devised priority functions that are suited to multiple criteria. How? Well, instead of the simple genetic programming selection algorithm, we use different available multi-objective evolutionary algorithms, like the well-known NSGA2, NSGA3, or different variants. And in this way, we obtain not one, but a Pareto front of priority functions that are customized to satisfy as many different criteria that we are defined to be able to build our schedule. We have experimented with at least 2 up to 9 criteria to be optimized simultaneously. Regarding the correlation of these criteria, we obtained very promising results. And finally, it is also possible to construct ensembles of dispatching rules to satisfy multi-objective scheduling problems, and this combination yields best performance so far, according to our findings. So we may combine these methods to solve multi-objective problems in an ensemble learning setting. So what has been done until now using this approach? Apart from single machine job shop scheduling and parallel unrelated machine schedulings, other scheduling problem variants have been tackled with this approach. For instance, there have been work on resource constraint project scheduling, on order acceptance and scheduling. A problem with scheduling with variable machine capacity has also been solved, in which the capacity of the machines or the number of jobs it can process in parallel varies over time. This is linked to the charging stations of electrical vehicles because there is a variable capacity in charging capacity. And there are similar, not combinatorial optimization problems that can also be solved with this approach. This has been applied to the vehicle routing problem and to the electrical routing problem in some new publications, or to the capacitated arc routing problem, traveling salesman, and bin packet problem. The usual suspects have also been tackled with this approach. This generally makes sense. Remember, if we are talking about online scheduling in dynamic environments, in that case, this approach will be very useful even on those problems. So instead of a conclusion, I do try to keep things on time here because it's either early morning or late in the evening. The performance of these automatically generated dispatching rules is in most cases better than those of manually designed dispatching rules, and of course definitely better when there are no appropriate manually designed dispatching rules for a specific scheduling problem that we are trying to solve. However, there are still issues, of course, as with any problem. We still do need some amount of domain knowledge to be able to apply this efficiently. Any bit of domain knowledge is, of course, always useful. This mainly relates to selecting the features that are used in building the dispatching rules and in building the priority function components. I mentioned earlier that the neural networks are not interpretable. Well, genetic programming is a white box model of sorts, but the interpretability could still be a question, because we may obtain priority functions that look like something that the human would never design. Let's be honest about it. And so how do we interpret those mathematical expressions? In that way, in that regard, we may apply different simplification algorithms, either after the evolution to simplify the expression we have obtained, or during the evolution to try to maintain the solution size and the solution interpretability to a high level. We may also restrict our priority functions to dimensionally aware genetic programming, but I will not go into details here. Ask me about it if it rings a bell. It can also be applied to stochastic scheduling environments very naturally, because we also approximate what the schedule is going to look like, and then when exact parameter values are known, we can quickly react to changes. The evolution speed is still a problem, because we need a number of test cases, and we need a number of generations, we need a number of trials and errors, evaluations to be able to obtain a quality priority function. However, this can also be done, always be done in an offline setting when we have time in advance. There is also the problem of selecting the appropriate dispatching rule. Even in our case, we wouldn't want, or we won't be able to evolve a different dispatching rule for any problem instance. However, we may devise a model to select what would be the appropriate dispatching rule, if we have many of them involved, to apply on a specific problem instance. We may use the features of a specific problem instance to try to derive a machine learning model that would select the appropriate dispatching rule among the ones that we have already evolved to be used to solve a specific problem instance. It works. However, there are many parameters to tune, and the efficiency is not always the same. And the most of the experiments that we do are, well, to be honest, they are mostly executing on synthetic benchmark problems, and we lack real-world applications. That is always the case in our academia setting. We lack more examples of real-world applications to see and to try to gain more insight in the performance of this model, and to try to see which techniques do really pay off in world setting, and which are actually not that effective. So after this slide, we come to the end. There are, of course, 42 slides, because that is the answer. And at this point, I would like to thank you for your attention, and please, you can begin with the questions.
Yeah, thank you. Thank you very much, Domago. That's a very comprehensive talk with a lot of different directions and aspects. Yeah, now we are the Q&A session. I already see a question on the chat. It says, thank you for your wonderful speech. I have one question. Why use a subset of instances can be used as a surrogate method on page 30? I think that's a question related to page 30, the surrogates method.
Yeah, that was my mistake, because I probably wasn't very detailed here. Okay. Just bring that slide. No. Okay.
41 at the moment.
No, I just want to bring that slide. Here we are. So no. Actually, these are different topics. We can use the subset of learning problem instances, or we can use a surrogate model. So these are actually different things, but in my talk I was probably not very clear, so I apologize for that. I meant those as a different candidate potential possibilities. So these are actually different things. Surrogate models are better. In my experience, surrogate models are usually better than using a subset of instances, but that's one of those things that only comes after, well, that's called wisdom, after a great many of failures.
Yeah, I think using, in addition to the surrogate model, we also have some kind of fidelity models. Maybe this is similar to different levels of fidelity to reach different accuracy of the estimation, right? Or the evaluation. Yeah. Fang got another question also about this page. Why surrogate can help get simpler rules? Because you mentioned this surrogate
Mhm.
model has an
Yes,
advantage, right? Yeah.
Well, not by itself. The surrogate model by itself does not need to, of course, to provide simpler rules. However, in some applications, it was just noted as a byproduct. It was noted as a byproduct, and of course, we can actively try to limit the solution size, which is the usual approach. We always have a limit for a solution size when using genetic programming. However, when using either subsets or using either surrogates, the rules we tend to evolve are generally less concentrated on a specific set of instances, and they tend to bloat less, which is, I suspect, a GP thing, and it's not generally, this could not be generally said for other methods of constructive priority functions, but I suspect this is a genetic programming issue that is related to the evolution algorithm that we are actually using and the selection method that we are using in this case, I suspect.
Thank you. Oh, it seems like this page 30 got a lot of questions.
Oh, wow.
Do you think different instance rotation setting might have an influence on GP performance? Which instance rotation setting do you recommend?
Oh, different instance rotation settings. I'm afraid I do not know this by heart. I'm afraid I do not know it by heart because I only applied one rotation instance technique. So I'm afraid I won't have the answer to this question by heart. I suspect there, of course, may be an influence, but I'm sorry, I'll have to look that up. I would have to look that up later on to be able to recommend a specific instant rotation technique. I'm sorry.
Yeah, probably also depending on different scenarios, I guess.
Yes.
Yeah. Oh, yeah. Got another long question.
Oh, by Tony Stark. Oh, nice.
Yeah.
Hi.
Machine learning. Tony Stark. The airman is here.
Mm-hmm. So this is a question regarding the topic that we all are very acquainted in the last year using deep learning and reinforcement learning. Yes, we did have a talk in this webinar series about reinforcement learning before. It was in the autumn, I think. Yeah. Yeah. And having seen the talk, I do think that we are going to see good things, good results from reinforcement learning and especially deep reinforcement learning in scheduling. I myself haven't applied many of those. Some of my students have, but yes, I do believe we may obtain very good results applying that technique. Now, that is, of course, regarding only the performance. But if you would like to see some, if you would like to obtain some other properties in your scheduling method, like to be able to see why it made different decisions and so on, then this may be an issue because deep models are, of course, generally harder to interpret. There are also advantages in that case, but yes, I believe we haven't seen the last of deep reinforcement learning in scheduling problems yet.
Yeah.
So I guess that's a thing. That's a thing to try out, definitely.
Yeah. I think I can share a little bit of my opinion as well. Also, nowadays more and more reinforcement learning. Actually, you can see more and more work in this domain. Actually, last year I also asked Yogan about this question. Yogan Blank. Well, during his talk, I also asked, how do you see the difference between reinforcement learning and GP. And he also said something like, the main difference is on the way to train. In fact, the outcome is really just the priority rule, or the decision-making policies. So the solution of reinforcement learning and GP actually the same thing. It's just how it learns. And I think Yoga mentioned there's in reinforcement there are two types of learning. One is is that model free and model based. I couldn't quite remember. Policy gradient, and kind of or value based or something. I think I think that the policy search is very similar to what GP does, but the others, value based probably is more different. So I think this is a very kind of big area that both our GP community and also the reinforcement deep learning community has a lot to explore, because originally these are kind of two different communities, and yeah, and then
it shouldn't be that way.
Yeah, it shouldn't be. So we should recognize the work done by each other and see the pros and cons of each other, and probably also can take advantage, borrow, learn from each other, to get some better results. We are doing something. Actually, we didn't see much direct comparison, so we are currently doing some work. Yeah, we are currently doing some work, try to directly compare reinforcement and GP to see what will happen if we directly compare them. That would be hopefully some interesting work there. Yeah, so some of my 2 cents. We should continue with the questions. Questions.
Thank you. There is another question. I see it in chat. The simplicity of evolved rules and accuracy are usually conflicted. Usually, yes. Simplicity is highly related to interpretability. So how do you think of the and accuracy? Usually conflicted. Yes, there's this notion of the simpler, smaller solutions that tend to generalize better. It's not always true, unfortunately, but this is just a rule of thumb, rule that is not always true, but we do tend to like more simpler solutions, that is to say solutions that are of smaller size, and simplicity is of course easier to interpret. We have applied different simplification techniques, and it turns out that the solutions that we obtained with the GP, although rather large, originally evolved by GP, can actually very efficiently be reduced to much smaller expressions. So there is a much smaller expression usually hiding in a large one that we obtain after the evolution, because the genetic programming doesn't take care of that during the evolution. But in most cases, in most individual rules that we try to simplify after the evolution, there is usually much space for simplification, and that simplification can be exact, to just eliminate different parts that are arithmetically still the same, or it may be approximate, that it's not generally the same expression but still behaves the same when solving this problem. So I think the size of the solution is not the main problem here, because in our experience, that size can be efficiently reduced during or after the evolution. There is another question. Well, I have a question. What is the meaning of appropriation DR in the context of conflicting objectives or many objective problems? How do we select features in the high dimension spaces? Well, for the multi-objective optimization, we usually we can also stick with the same features we used in the single criterion problem. However, for different criteria, different features are simply not relevant. And in most cases, luckily, it is very easy to identify features that are completely irrelevant to us to a certain scheduling criteria. So if we don't optimize for that criteria, we don't have to use that feature. However, if I remember correctly, in our experiments, we do need to combine more features to obtain solutions to multi-objective scheduling problems. So in this context, it is always harder to evolve for multiple objective problems. That is true. How do we select features? Well, that's a different question. But luckily, the selection of features can be performed with the techniques that are orthogonal to the problem at hand.
Mila, do you have a question? I see you are unmuted. No. So do we have any other questions for Domago? We still have a few minutes left. Oh, actually, maybe I can ask a question using the last few minutes. You mentioned this static problem, right? Also that's the dispatching or GP to learn dispatching rules for for static scheduling problems, because we have so many very tailored and also promising algorithms for the static scheduling problems. What would be the reason, for example, for us to consider GP? Why should we consider GP to solve static scheduling problems?
Yeah, you're right. You're right. In a static scheduling problems, we can just search away, and if we have a lot of time, we can search more, and eventually we will come to the solution that satisfies our criteria. That's true. If we have a lot of time, then really we don't need this approach. We can use existing meta heuristic improvement heuristics. However, in a specific, there's always a specific. In a specific case that where time is an issue, in the sense of we do pay for time, because time is not money. Time is much more valuable than money. In those cases, we may still have the liberty to choose between different with different variants, with different I forgot the word. Sorry, with different aspects of satisfying those two criteria, and be able to choose the technique that is actually more efficient in the same amount of time. So it may be that in a same limited amount of time, which is longer than in dynamic scheduling, but still shorter than what we are what we can allow ourselves. In that short amount of time, we can still have better convergence, and better solutions can be obtained than the usual meta-heuristic methods. And of course, there's the method that we use to build the schedules, and it is still incrementally built. So if a situation occurs where there is a change in the system, then we can just reapply the same method to build the remainder of the schedule, and to obtain the solution in this time that we have available. So it is still applicable in conditions where we allow for changes in the environment.